Good morning. This is lesson 44. Is my quarter a fair bet? Previously we worked on claims with a penny, and now we're going to do a complete 4-step significance test. So we found a quarter, we started to flip it. We think it's biased, probably because it's bent. Seems to be biased toward tails. It was flipped 80 times and we got heads only 33 times. Now 33 out of 80 is 0.4125. So we can work with that number, or we can work with its complement, which is 1 minus 0.4125. The complement of that is 0.5875. Now, it makes a difference as far as the direction of our inequality goes in the null hypothesis, or rather the alternative hypothesis. If we're going to go with 0.4125, we would go with less than. So we want that or more extreme. But if we wanted to go with 0.5875, we would use a greater than, there or more extreme. It just depends on which side of 50% we're talking about. So our parameter, our p-value, that's the true proportion. Okay, I'm going to stick with heads. The true proportion of heads. So I am going to be using the number 0.4125. If I wanted to use 0.5875, then my parameter would be defined as the true proportion of tails. The statistic then is this 33 out of 80, or 0.4125. We're going to stick with a significance level of 5%. Our hypotheses are, first of all, the null is that the coin is fair. That means 0.5, 50-50. But my alternative is that it's not fair. And in fact, it's less than what it should be, 4 heads. This is the importance of defining the parameter, to know which numbers we're talking about. Again, this is not where we put in the statistic. Hypotheses are always about parameters. So the procedure is a 1-sample z-test. That would make a big difference if we were using a graphing calculator. It would tell us which tests to use, which buttons to press. For us, though, just means that we're going to use the correct formula for standard deviation. Now, since we're talking proportions, we have 2 situations or 2 conditions to check. Number 1, is this a random process? And it is, because flipping coins is assumed to be random. The second condition is large counts. That's going to enable us to be using the z-chart or the z-table. So large counts, we're going to use the hypothesized values here. The hypothesized values are, if we do 80 coin flips and it really is 50%, we should get 40 heads and 40 tails. You do not use the statistic here, because we're assuming the null is true until we have evidence otherwise. The mean is the center. The mean with respect to that statistic is still the hypothesized number, 0.5. The standard deviation has its own formula. The standard deviation with respect to p hat is going to be the square root of p, 1 minus p, over n. Again, we're using the hypothesized null value of p instead of the statistic, because we don't know if the statistic is the center. We don't have evidence of that yet. We may or we may not. So now it's time to calculate. Multiply 0.5 times 0.5. You get 0.25. You divide that by 80. And finally, you take the square root. And it's 0, 5, 6. So between 5 and 6% is one standard deviation. That's going to help us to draw the picture of the normal curve. So the normal curve, and we're going to just label a few things. The center is 0.5. Our statistic, now we bring that in, is 0.4125, and that's going to be about 2 standard deviations away. So I'm going to draw it over here. 0.4125. We want to know what is the probability of getting something this extreme or more, assuming the null is true. We're still not ready to contradict the null. So that area right there. That means that we then need to find a z-score. The general formula, and this works for not just what we're doing now, but other tests, is that it's the statistic minus the null divided by the standard deviation of the statistic. But specifically in our case, that just translates to a z-score. So the p-hat is going to be 0.4125. The p is a hypothesized value of 0.5. And the standard deviation, 0.056. Which gives us negative 1.56. It's time for us to use the z-chart and look up this value, negative 1.56. Okay, and the value appears to be 0.0594. 0.0594. We are not subtracting that from 1 because from our picture we do want the area to the left. This is our p-value, not the hypothesized proportion. This is a different p-value. This is the probability that, assuming the null is true, we get a result as extreme as 0.4125. So our test statistic was here, and our p-value is here. Now we make the conclusion. Based on that p-value, is that p-value low? Is it less than 5%? No, it's actually a little bit more than 5%, almost 6%. So then we say, since 0.0594 is greater than 0.05, we fail to reject. We never accept, we fail to reject. Now, let's put some context in there. What are we talking about? We don't have convincing evidence. The coin is not fair. It's just like a jury. You can't say, we've proven this defendant innocent. What you say is, we have rendered a verdict of not guilty. We do not have the evidence of guilt. Now, this was a 4-step process. Let's go back and look at the steps. Step number 1, state. We state what is our step 1. We state what is our parameter value and what are the hypotheses. Plan. We figure out what kind of test we're going to do, and we look at the conditions. 3, we actually do the test. We do the work. Let's restate that in the notes. So, 2 things, really. Number 1, state, parameter, hypotheses, and by the way, we also stated the level, which was 5%. Plan, name the procedure, and also check conditions. Do, it is always a good idea to include a picture and put in the work, the calculations you used. And finally, conclude, make a decision. In context. In context means include details about what is this about. Number 2, if we were going to do a 2-sided test, and that would be when the null states the parameter, but the alternative simply says P is not some value, the picture will look like a symmetric area on both sides. We simply double the area to find the p-value. Now you have the opportunity of practicing that 4-step process on the next problem, Who Feels Job Stress?